Welcome to the deep dive. Today we're getting our hands dirty, metaphorically speaking, with fermented compost tea.
Yeah, that whole idea of soaking weeds in water, is it legit plant food or just garden hype?
Exactly. We're looking at Kesser and Steen's exploration here. They were asking the same questions you might be.
Right, they even talked to Professor Hendricks from their Nature and Innovation class. So we've got some decent info to unpack.
Their starting point was super simple, wasn't it? Literally just weeds, water, bucket.
Pretty much, like making tea, but, with dandelions instead of Earl Grey.
Huh. Right. So our mission here is to figure out if that basic method, and maybe some fancier ones, are actually worthwhile for your garden or just, interesting to know about.
Yeah, cutting through the noise. We'll cover the basics, the science, nutrients, microbes, that kind of thing.
And this idea of biological synergy sounds intriguing. Plus KNF extracts and how this all scales from a window box to like a farm.
Let's dive in.
Okay, so Kesser and Steen's weeds in a bucket idea, Professor Hendricks weighed in on that.
He did. He basically said, yeah, that simple act, soaking plants, especially weeds, in water. That is the fundamental way to get started.
Really? So it actually works?
Well, it works to extract something. The water pulls out soluble nutrients, stuff that dissolves easily, and some microorganisms that were on the plants.
So Kesser and Steen weren't totally off base with their initial hunch.
Not at all. He confirmed it's a usable method. Fits right into permaculture, too, using what's right there. You're just recycling readily available resources.
That makes sense. No fancy gear needed for round one.
Exactly. Just weeds you probably wanted gone anyway.
Okay, so what's actually happening in that bucket while it's sitting there? It's not just teeping like tea, presumably.
Right. It's decomposition. But because it's just sitting in water, there isn't much oxygen, so it's a slow breakdown. Fermentation, maybe gentle rotting.
Does it smell?
Oh, it definitely can, yeah.
Yeah.
Professor Hendricks mentioned that, but he also said a bit of an odor doesn't automatically mean it's bad or useless, just means things are happening.
Good to know. Because, yeah, the smell could put you off. Are some weeds better than others for this? Like, should I be hunting specific ones?
Yeah, some are richer in certain things. Professor Hendricks pointed out nettle's great for nitrogen, iron. Dandelions, ground elder too. They tend to pull up lots of minerals because of their deep roots.
Turning pests into potions. I like it.
Oh.
Okay, so after, say, a week or two, what's the next step?
You strain it, get the liquid out, leave the sludgy bits behind.
And that liquid, that's the tea.
That's the tea. You can use it to water your plants, maybe dilute it, maybe use it straight, depends how strong it seems. Some people even use it as a foliar spray on the leaves.
Okay, basics covered. But let's get nerdier. What's the science? Why might this actually benefit the plants beyond just giving them a drink?
Okay, so microorganisms, they're naturally on the plants, right? In the water, they start breaking down the plant cell walls.
Okay.
And as they do that, they produce stuff. Short organic acids, mainly. Think like acetic acid in vinegar or lactic acid in yogurt.
Acids? Are those good?
They can be. First, they lower the pH a bit, which can actually stop some bad microbes from taking over, like a preservative effect. And second, these acids can make certain minerals in the tea more soluble, easier for plants to grab onto.
So unlocking the nutrients that are already there.
Exactly. Professor Hendricks also mentioned that during active fermentation, especially if you have things like lactic acid bacteria involved, maybe from adding a bit of bokashi bran or something,
Right.
nutrients like calcium, magnesium, potassium can kind of temporarily bind to these organic acids, or even tiny bits of protein, amino acids, that come from the plant breakdown.
Amino acids. Kesser and Steen had a thought about that, didn't they? Something about easier transport.
They did.
Yeah.
And Professor Hendricks said, yeah, that's totally plausible. Plants often find it easier to absorb nutrients when they're attached or chelated to organic molecules like amino acids.
It's like a little delivery package.
Sort of. It helps them get through the plant's cell membranes more easily. And it might stop them getting locked up in the soil quite so fast.
So it's not just what nutrients, but how they're presented.
Precisely. Bioavailability. That's the key word. These nutrient packages can be taken up by the roots or maybe even the leaves if you spray it, especially if it's diluted.
Fascinating. It's like microbial predigestion for plants. What about these microbial metabolites Professor Hendricks mentioned?
Right, so that's other stuff the microbes produce. Not direct food, but things like enzymes, vitamins, signaling molecules, growth stimulants, basically.
And stimulants? For what?
They can help with root growth, maybe improve the plant's stress response, influence the microbial community right around the roots. It's complex stuff.
Okay, so even if you tested this tea and the NPK numbers were low,
Yeah, nitrogen, phosphorus, potassium.
they'd still be doing a lot of good.
That's what Professor Hendricks was emphasizing. The real value isn't always in those big NPK numbers. It's in the bioavailability, the living dynamics, this biological synergy.
Synergy.
Yeah.
The plant, the microbes, the organic compounds, all working together.
Exactly. It's an interaction. He did caution, though you need to monitor it. Check the pH, maybe with indicator strips. And don't go drenching delicate seedlings with super strong, oxygen-poor, stinky liquid.
Common sense, right?
But yeah, used thoughtfully, it's a sustainable, creative garden supplement. It's a liquid rich in dissolved organic compounds and microbially processed nutrients, not just basic fertilizer.
Okay, and this connects back to permaculture you mentioned.
Definitely. Permaculture often focuses on the microbiology, not just nutrients in isolation.
Right, building healthy soil life.
So Professor Hendricks talked about supporting active microbial cultures like fermenting herbs in rainwater, or maybe adding a handful of good compost or soil, or even something sugary like molasses to feed the microbes.
So actively trying to cultivate the good guys.
Yeah, and that leads to a distinction he made. There's the simple anaerobic fermentation weeds in a field bucket, low oxygen.
What we've mostly been talking about.
Right. And then there's more advanced aerobic compost tea. That's where you actively pump air into the brew or stir it a lot. The goal there is to multiply aerobic oxygen-loving microbes.
Is it more complicated?
It is. Requires equipment. But Professor Hendricks noted the simple anaerobic version can still be useful, especially if you use it relatively quickly. It's a low-tech approach, common in permaculture circles.
So, experiment, observe the plants, trust your nose a bit.
That was his advice. See what happens. Is it helping? Does it smell okay or truly awful?
Professor Hendricks also brought up the carbon cycle. How does that fit in? Felt like he was saying this goes deeper than just fertilizer recipes.
Absolutely. He stressed that fertilization isn't just NPK, it's the whole cycle. Carbon is central, and the interaction with microorganisms is crucial.
So Kesser and Steen were onto something more fundamental.
He thought so, deeper than most fertilizer guides go. The idea is that living soil accustomed to these kinds of fermented inputs and natural cycles, builds resilience.
Resilience how?
Plants grown in that kind of environment might handle drought better, resist pests more effectively, cope with sudden changes. It's not the immediate hit you get from synthetic fertilizer.
Right, not that instant green up.
No, it's slower. It's about nurturing the whole ecosystem, building health over time.
Okay, and this ties into the liquid chop and drop idea. Explain that again.
Right, Professor Hendricks' term. Making weed tea is like taking the plants you chopped, the weeds, and dropping them back, but in liquid form. You're extracting what those weeds pulled from the soil.
NPK.
Yeah, but also calcium, magnesium, sulfur, iron, trace elements like manganese, copper, zinc, all that stuff.
And weeds are good at this.
Often, yeah, especially deep-rooted ones. They can access elements deeper down than, say, your lettuce plants.
Like nettles grabbing nitrogen and iron.
Or ground elder being good for potassium. He used those examples. But he also reiterated, you probably won't know the exact amounts without a lab test.
And high concentrations aren't really the main point anyway.
Exactly. It's more about the mix, the process form, the microbial life.
So thinking of it as a living connection to the soil, that opens things up.
It does, because plants aren't passive. They create connections. They release those root exudates we mentioned, sugars, organic acids.
Extract microbes.
Yeah, to sort of trick or partner with fungi and bacteria to get minerals or protection or better water access. It's a whole symbiotic dance.
Okay.
So the idea is if you add extracts from other plants that have already done the hard work of gathering nutrients and maybe feed the microbes with sugar or molasses during fermentation, you might stimulate those same symbiotic relationships in your own soil.
Whoa, okay, that's complex. It's like giving your soil a boost of pre-negotiated deals.
Now, things got really interesting when they started talking about specific weeds from specific places, like nettles from a swampy bog near an ochre stream.
Okay, that sounds oddly specific. Why there?
Because location matters hugely for nutrient content. Nettles growing near an ochre stream. Ochre is basically iron oxide. Rust suggests the subsoil is super iron-rich.
Ah, okay. Makes sense.
And in boggy, swampy soil, you have layers without much oxygen. In those anaerobic layers, iron dissolves, becomes mobile iron too. When that water hits the air, the iron oxidizes, turns into rust-colored iron through the ochre.
Right.
And often, where you find iron like that, you also find manganese. They hang out together in those conditions.
Okay, so these bog nettles are potentially full of iron and manganese.
Very likely. Now, there's a twist. In oxygenated conditions, iron and phosphorus can bond really tightly, forming iron phosphate, which makes the phosphorus less available to plants.
Oh, okay, so lots of iron isn't always purely good.
It can lock up phosphorus, but fermentation, especially with things like lactic acid bacteria or just the lower pH, can help remobilize some of that iron and phosphorus, maybe as chelates, bound to those organic acids.
So the fermentation could actually unlock nutrients that were stuck.
Potentially, yeah. And manganese is often available in its soluble form, MnEI, in those wet, low-oxygen bog soils before it gets oxidized.
And manganese is important.
Crucial. Especially for things like peas and legumes, they use it in photosynthesis and nitrogen fixation.
Wow. So those swamp nettles weren't just giving nitrogen. They were potentially offering a whole trace mineral brew iron, manganese, maybe freed up phosphorus, all thanks to where they grew and the fermentation process.
Exactly. A hyper-local nutrient boost.
This sounds like Kesser and Steen were kind of blending different ideas together.
Professor Hendricks praised that. He saw it as combining elements of traditional compost tea, Korean natural farming, or KNF, and even local geology, understanding the soil where the weeds grew.
KNF, what's that involve?
Korean natural farming often uses fermented plant extracts, sometimes using brown sugar to help fermentation, and focuses heavily on indigenous microorganisms. Kesser and Steen seem to be experimenting with similar ideas.
Okay. And they were thinking about adding clay, too, from coastal cliffs. Why clay?
Adding clay, especially to an arided tea, can be really beneficial. Professor Hendricks mentioned a few reasons.
Like what?
One, it provides massive surface area, like a scaffold for microbes to attach to, helps them colonize faster.
Okay.
Two, if it's calcareous clay, from chalky cliffs maybe, it adds calcium and magnesium. Three, clay has colloidal properties, tiny particles that can help stabilize micronutrients, keep them from locking up.
So structure and nutrients.
Yeah.
Any other benefits?
It can also buffer things, maybe bind excess ammonia or even heavy metals, especially if the swamp nettles were really high in minerals. It adds a layer of safety.
Makes sense. And using a KNF-style ferment as a starter culture.
Yeah, like using sourdough starter for bread. You're introducing microbes already adapted to breaking down plant material, possibly specific to the local environment. It can lead to a faster, more stable fermentation process.
So the KNF starter microbes and the aerobic microbes in the aerated tea might work together.
Potentially, yes. You could get synergy between the lactic acid bacteria and yeast from the starter and the aerobic bacteria and fungi you're breeding with the air pump.
They were also checking pH, right? Using red cabbage, does that actually work?
Oh yeah, red cabbage juice is a classic natural pH indicator. It changes color depending on acidity. Professor Hendricks confirmed it works well, especially with rainwater or tap water.
What colors are we looking for?
It goes from blue or purple in neutral or slightly alkaline conditions towards pink and red as it gets more acidic. As the microbes produce acids during fermentation, you'd see it shift towards red.
Cool. And is there an ideal pH?
Often, a pH around 6 to 6.5 is considered a good balance for many compost teas, acidic enough to be stable, but not so acidic it harms plants.
Okay, back to the carbon cycle. How does the fermentation itself fit in there?
During that anaerobic or semi-anaerobic breakdown, the microbes release not just acids but other simple carbon compounds. Professor Hendricks called it an upstart spec, a starter pack.
A starter pack for what?
For the soil microbes. When you add the tea to the soil, you're giving the existing soil life a little energy boost, some easy food to get them going.
So it kickstarts activity in the soil itself.
Exactly. Their mini fermenter project, he suggested, wasn't just about making fertilizer in the traditional sense. It was demonstrating this broader concept, recycling plant resources to initiate a carbon microbe nutrient cycle. It tells a story about how even weeds fit into the bigger picture.
They also mentioned ground elder, calling it inland seaweed.
Yeah, that's a good way to put it. For people who don't live near the coast and can't easily gather actual seaweed, ground elder is everywhere, has deep roots, accumulates nutrients. It's a readily available resource.
Unlike actual seaweed, which is amazing if you can get it.
Oh, absolutely. Eelgrass, bladderwrack, fantastic as mulch. They add nutrients, retain moisture, suppress weeds, feed soil life. It's a coastal privilege, really.
Steen even saw potential in that sargassum washing up in Florida, right? The smell of money.
Yeah. If it could be processed into soil improver. Big challenges there, obviously, the smell, logistics, public perception. But it highlights the point. Valuable resources are often nearby if you look with an open mind, even weeds.
Steen had other ideas too, like selling dried weeds.
Bit entrepreneurial. Selling them as herbal tea ingredients.
But Kesser brought it back to manganese, saying it's more complex than just pH.
Right. This is a really important point, especially in organic systems. Manganese deficiency can happen even if there's manganese in the soil.
How?
Often because the soil becomes too aerated, too oxidized, especially lighter, sandy soils low in organic matter. Improving soil health, ironically, can sometimes temporarily lock up micronutrients like manganese.
Wait, improving soil locks up nutrients? That seems backwards.
It's because the increased microbial activity can convert the manganese into less soluble forms, especially if the soil's cold, like in spring, when the microbes aren't super active yet to release it again.
And some plants really feel this.
Peas and other legumes are super sensitive. They might get yellow leaves, poor growth, weakened nitrogen fixation. Manganese is vital for photosynthesis and for enzymes involved in that root nodule symbiosis.
So yellowing peas might not mean lack of manganese in total, but lack of available manganese.
Exactly. It's all about availability, which is heavily influenced by redox conditions, the balance of oxygen and moisture. Dry, loose, sandy soil makes it hard for plants to take up manganese.
Professor Hendricks used an analogy: iron and manganese as siblings.
Yeah, reacting sensitively to changes in oxygen and acidity, sometimes competing. It's a delicate balance.
So Kesser and Steen could actually test this with their pea experiments.
That was the suggestion. Grow peas in different soils, maybe one with seaweed compost, one with ground elder tea added, one plain, and just observe. Look for differences in leaf color, growth.
Should they add manganese?
Probably not directly in large amounts. Maybe add a source of trace elements like crushed granite or dried seaweed. The key isn't usually adding more, it's improving the availability of what's there. Yellowing peas are a signal that availability might be the issue.
Can you break down the chemistry bit? Manganese oxidation states.
Sure. Manganese, like iron, changes its chemical form depending on oxygen levels. In well-aerated, oxygenated soil, it mostly exists as insoluble oxides or hydroxides, MNIV forms like MnEORO. Plants can't really absorb that, it's bound.
Okay, unavailable.
But in wetter, oxygen-poor, reduced soil conditions, that MNIV gets reduced to soluble MnU, the M ion. That's the form plants can take up easily.
Just like iron changing from Fe to Fe.
Exactly the same principle. Redox potential is key.
Does phosphorus play a role here too?
It can. High phosphorus levels, maybe from lots of manure or phosphate fertilizer, can lead to the formation of poorly soluble manganese phosphate compounds, locking it up again.
And other nutrients compete.
Yeah, Mu competes for uptake with other positive ions like calcium, Ca, and magnesium Mu, which are often abundant in soils that have been limed or heavily manured.
So different soil amendments have different effects on manganese.
Right. Manure might bind it up because of the phosphorus and calcium, but deep-rooted cover crops could improve availability through their root action and decomposition.
And Kesser and Steen's willow compost base.
Professor Hendricks thought that was a good, fairly neutral starting point for their experiments. Adding dried seaweed would be great for long-term micronutrients, manganese, zinc, boron, iodine.
They used LECA balls, too.
Yeah, for aeration and drainage in the pots. But maybe the missing piece, Professor Hendricks hinted, was those organic acids from fermented teas to help keep micronutrients soluble.
What about the color changes in their red cabbage test? Did that mean anything beyond pH?
Professor Hendricks speculated it might. Color changes, especially bluish tones and slightly alkaline conditions, can sometimes indicate reactions with transition metals like copper or manganese, forming complex compounds. It's subtle, but worth observing if the colors shift strangely when they add different extracts.
Are there plants particularly good at accumulating manganese that they could use for tea?
Yeah, besides nettle, which we mentioned is good for manganese and iron, things like dandelion, horsetail, alfalfa again, often deep-rooted plants are known accumulators. Using teas or foliar sprays from these could be beneficial.
So their garage lab setup. It's becoming a micronutrient starter project.
Kind of. Forget teddy bears at steel mills raising awareness. Maybe weed tea is the garden-scale solution for micronutrient availability.
Can you just quickly clarify that insoluble manganese form again? The MnOH.
Right, that and similar complex hydroxides. They form under oxidizing conditions when the mobile MO gets converted back to the insoluble MnIV state. They can behave like tiny particles or colloids in the soil.
And that's why sandy soils are prone to deficiency, especially in drought.
Exactly. Sandy soils often fluctuate wildly in moisture and oxygen, redox. They don't buffer well. And during dry spells, any manganese present gets locked up in that oxidized state. And the poor soil structure doesn't hold on to it well anyway.
And adding manure to sandy soil during drought could make it worse.
Counterintuitively, yes. Manure can release nitrogen and phosphorus quickly, pushing growth when the plant can't get trace elements. Plus, the manure might raise pH and add calcium and phosphorus, further binding the manganese. And sandy soil loses nutrients like ammonium easily anyway without enough clay or humus.
Okay, so what fermented extracts did Professor Hendricks seem keen on for them?
He liked their idea of self-fermented dandelion and nettle tea, low salt, lightly fermented. Good as a bioactive foliar feed, releasing nutrients and those chelating organic and amino acids.
And ground elder.
He called it a spring gift for microbes. Use it fresh or dried in ferments. Rich in potassium, magnesium, some manganese, especially if harvested from woodland edges.
And the rabbit droppings on willow chips.
A schoolboy's hack for regenerative growing, he called it. Slow-release nutrients, moisture retention from the chips, creating a mini permaculture zone right in the pot.
And using peas as indicators.
Yeah, while commercial key farming might focus on yield, peas are brilliant indicators for gardeners because they show deficiencies, especially manganese and molybdenum, quite clearly. They're sensitive canaries in the coal mine, so to speak.
Okay, final check. Adding clay to the fermented herb tea. Good idea.
Yes, Professor Hendricks affirmed that. Adding clay particles to the liquid extract itself.
Why does that help?
Again, huge surface area on the clay particles. They can bind nutrients and those organic acids from the ferment.
So the goodness sticks to the clay.
Right. And the acids in the ferment might even gently etch the clay, releasing some locked-up micronutrients from the clay itself. It also binds amino acids, sugars, making them available to soil microbes for longer.
Does it clump up?
Could do in standing water, but mixed into a porous potting mix, it should integrate well. It creates this microscopic substrate, he said, where nutrients, microbes, and water can interact effectively.
So it's like a clay chelate.
He proposed that term. With the organic acids doing the chelating and the clay providing structure, buffering, and slow release. He suggested it as an experiment. Compare peas grown in their willy rabbit mix versus the same mix with added ferment and clay.
So their pots are already like little ecosystems.
Essentially, yes. Professor Hendricks described their big pots as living aerobic microfermenters. Roots, microbes, fungi, nutrients, organic compounds all interacting.
Different from the fermenting buckets, though.
Totally. The buckets are warmer, wetter, less air anaerobic or semi-anaerobic. That warmth in the buckets, that's microbial activity, breaking down sugars and plant matter, generating heat like compost.
And the clay itself is a resource.
He called it a gold mine, especially if it has good cation exchange capacity, CEC. When it gets moist and acidified by the ferment, it releases ions and provides binding sites. Just, don't use pure pottery clay meant for crafts it won't drain.
Right. Good point.
Their whole experiment, he felt, shows how interconnected everything is. You can't just read about it. You have to observe the smell, the bubbles, the color changes, feel the living system.
Sounds like Kesser and Steen are really onto some exciting stuff. It's not just about following a recipe.
Not at all. Their slightly unconventional approach is revealing these hidden processes. You can just picture Oma's Terrace turning into this buzzing learning lab.
We should document it. Videos, hashtags.
Maybe. But the most important thing, Professor Hendricks implied, is their own evolving understanding. Questioning standard measures, thinking about life, diversity, connections, not just yield.
And they were already thinking ahead. Continuous fermentation.
Yeah, setting up a continuous bubble fermentation and aerated tea setup so they'd always have fresh plant juice for experiments, like a liquid compost on tap.
Clever. And using the excess liquid to see if it affects aphids.
That's smart observation, looking at plant defense mechanisms. And their KNF-style fermentation of beech buds, that's really innovative.
Beech buds, why those?
Buds in spring are packed with growth hormones, enzymes, phenols, everything the plant needs for that initial burst. Fermenting them with sugar helps release those compounds in a bioavailable form.
So it could be a growth stimulant or boost immunity?
Potentially, yeah. Similar ideas exist in biodynamics with fermented algae or other buds. He noted their description of a lively fermentation, like wine, made sense given the sugars and natural yeasts likely present on the buds. Maybe resins or saponins causing foaming, too?
It really does sound like a garage laboratory, guided by nature's recipes.
Exactly.
Okay, let's try and wrap this up. Key takeaways from this deep dive into Kesser and Steen's fermented tea journey.
I think the main thing is that these fermented teas, these extracts, they're much more than just simple NPK fertilizers. It's about complex biology.
Microbes doing work, nutrients becoming more available.
Right. Bioavailability, biological synergy, feeding the soil life, not just the plant directly. It's about building health over time, using local resources, even weeds.
So for you listening, that initial curiosity Kesser and Steen had, is this weed tea thing real? The answer seems to be yes, but it's way more interesting than you might think.
It opens up fascinating aspects of soil science, nutrient cycling, the power of microbes, using stuff that's probably right outside your door.
So a final thought then. What weeds or overlooked resources are growing near you? Could they become part of your own garden experiments? Maybe try a small batch, ferment yourself.
See what happens. Observe, smell, test it out. You might be surprised what you learn just by looking at your own patch with these ideas in mind.
Welcome to the Deep Dive. Today we're getting our hands dirty